Thank you very much or to the organizers for the very nice event. So as Kurush said, I'm going to talk about polystructure of Shintani zeta functions and Newton polytopes. This is part of my PhD, which I hope to finish next year. I really hope to. I'm really sorry for the mistake on the date. It's not a very good beginning, but okay. So this is the outline of the talk. I'm going to give a very brief introduction about zeta functions and explain what Shintani zeta functions are. Then I'm going to talk very fast about the Mellin transform, which will be our main tool to build a meromorphic continuation for such zeta functions. And then I'm going to talk about the Newton polytopes and the relation it has with the pole structure of the Shintani zeta functions. So let's start here. So the most known zeta function is the Riemann zeta function. I think most of you are familiar with it. It's originally defined like this. So for S, a complex number, this sum here is absolutely convergent whenever the real part of S is bigger than 1. And then Riemann proved that it actually can be meromorphic. It has a meromorphic continuation to the whole complex plane with a single pole in exactly at S equal 1. And there are several multivariable generalizations of such Riemann zeta function. One very popular are the multi-zeta functions, which are usually defined like this. So this sum in the middle. This sum is absolutely convergent whenever the real part of S1 up to Si is bigger than I. It has a domain of absolute convergence, and it was proved in 1999 by Zhao that it admits a meromorphic continuation, and later I think in 2000 it was proved by Akigami. Sorry, I forgot I'm terrible with Japanese last names. Yes, thank you very much. The precise polystructure of such multiple zeta functions. A third type of multivariable zeta functions are conical zeta functions, which can be defined in this way. Oh, sorry, I forgot to mention this. Another way of seeing the multi-zeta functions, these multi-zeta functions here, is by making a small change of variables. So the smaller variable n1 is equal to m1, and from there n2 is equal to m1 plus m2, and so on. So nd is equal to m1 up to md plus up to md. This way of expressing them is going to be useful for the rest of the talk. And yes, a third type of known multivariable zeta functions are conical zeta functions, which for a convex cone of this form, where VI's are vectors on set D with non-negative arguments, then we can sum over all integer points inside this cone. Yeah, that's another type of zeta function, which also admits a meromorphic continuation to the complex space C to the power D. Okay, but the Shintani zeta functions are a generalization of the three types of functions we saw on the last slide, and it's defined like this. So let's consider this to be the set of all n times r matrices with real non-negative arguments, such that there is at least one positive argument on each row and one positive argument on each column. Then for a matrix of that type, we can define the Shintani zeta function set A as it is expressed here. So where these small i's are the arguments of the matrix A, and we're basically each of these parentheses is each of the lines of the matrix A, will inner product with the vector m, so m1 up to mr. Such Shintani zeta functions are this sum on the right hand side is absolutely convergent whenever the real part of Si for each I is bigger than R being the number of columns of the matrix. Yes, so okay. So in 2014, Guo, Pei, and Shang proved that any conical zeta value is a linear combination of Shintani zeta values. When I say values instead of function, I mean that the S, the values of this S are integers, right? They actually prove something more general, is that the space spanned by conical zeta values is the same space spanned by Shintani zeta values. However, that is not known if it's true for Shintani zeta functions, so for any values of S. Okay, Matsumoto proved in 2002 that such Shintani zeta functions admit a meromorphic continuation to the whole complex space C to the n with linear poles. And what I want to tell you in this short communication is a refinement of this theorem, in which we have a very precise description of those hyperplanes which contain these linear poles. So here are some examples just to clarify what a Shintani zeta function is. In case the matrix is the identity, it satisfies all the requirements. It has non-negative arguments, and in each row and in each column, it has at least one positive argument. So for the identity, the Shintani zeta function related is just this, n times the product of the usual Riemann zeta function. If we have that A is such a triangular matrix with ones on the diagonal and under it, then we recover the multi-zeta functions. But it can be even more general, so if A is not a square matrix, then we have something like that, for instance. One other thing that I should mention here is that it is also known that any conical zeta function can be expressed as a sum of Shintani zeta functions. What is not known is the opposite, is if any Shintani zeta function can be expressed as a conical zeta function. Okay, so to talk about the meromorphic continuation of those Shintani zeta functions, I will briefly recall what the Mellin transform is. So given a measurable function from Rn to R, then the Mellin transform is defined as this integral here. The domain of convergence of this integral depends on the function g. So, for instance, consider this exponential sum. It is known that for the usual Riemann zeta function, the Mellin transform of this sum we have here, it's equal to the Riemann zeta function times gamma of S. So it is a known result. In the case of Shintani zeta function, something very similar happens. So if we define this other type of exponential sum, it's just a generalization of the one we had before. Like here is an example. We can also express the Shintani zeta function just as a quotient of the Mellin transform of S of A over gamma of S. Here I am making a little abuse of notation, where gamma of S is just the product of the gamma of Sj for each j. And here epsilon s minus 1 is just the product of aj, epsilon j to the power Sj minus 1. So, so then finding a meromorphic continuation and a polystructure of the Shintani zeta function it's equivalent to finding a meromorphic continuation and a polar description of the meromorphic transform of SA, right? So now Newton polytopes, the last ingredient. So let me recall what Newton polytopes are. So given a Laurent polynomial, sorry for the terrible French pronunciation, of this type, so where A is a finite subspace of set n, so see that we allow here alpha to have negative integers, so we can have negative powers. Then the Newton polytope of this polynomial is just the convex whole generated by the exponents. Let's see an example. So if this is our polynomial, we have a polynomial with three monomials. We take the exponents of each of the monomials, and they give us the coordinate of this triangle. So 2, 1 is this here, then 1, 3 is this here, and 2, 2 is here. So the Newton polytope is this triangle, of course, with the area inside of it. Also a reminder, it is known that any polytope, any convex polytope, can be also represented alternatively as the intersection of half spaces. So for the example we had before, we can see this triangle as the intersection of this half space, which is the half space from that contains this facet and goes into that direction. The second one is related to this facet and goes in this direction, and the third one this facet and in this direction. So where these mu k's are important and these nu k's too. So these mu k's are integer vectors in the inward direction of the facet, right? Orthogonal to the facet in the inward direction of the polytope. Okay, so what do Newton polytopes has to do with the Mellin transform and with Shintani zetas? Well, I recall a theorem by Nilsson and Passari in 2010, which says that the Mellin transform of 1 over p, from p being a completely non-vanishing polynomial, I'm not going to explain what completely non-vanishing is, then this Mellin transform is absolutely convergent on this tube domain. So whenever the real part of S is on the interior of the Newton polytope. I find that a very nice theorem because we have a geometric description of the domain of convergence of this Mellin transform. However, for our purpose, we need to adapt this theorem a bit. So precisely, we need the case where we have here on the numerator a rapidly decreasing function. So we proved this year that the Mellin transform of phi over p, where p is a bounded measurable rapidly decreasing function. So you can think in a Schwarz function, for instance. Then the tube domain, the domain of convergence and analyticity of this Mellin transform, it's given whenever the real part of S is on the Newton polytope of P plus Rn plus. So let me show an example. For the polynomial we had before, if we multiply on top by a rapidly decreasing function, then the new domain of convergence amounts to this red area we have here. Notice an extra of this theorem is that with the original theorem by Nilsson and Passari, so if the Newton polytope of P had empty interior, then the Mellin transform converges nowhere, while here, even if the Newton polytope is a point, so P is just a monomial, then the Mellin transform of phi over P is, well, it's quite big. It's an unbounded set. And here is my main result. I don't want to take more time than necessary. So if we have a matrix of the types we've described before, so with non-negative arguments and at least one positive on each row on each column, all those requirements are needed for this sum to make sense, so for the Shintani zeta function to make sense. And consider J any subset of 1 to R, so where R is the number of columns of our matrix A. And consider this expression, say J of epsilon, which is just the product of, well, the linear forms induced by the columns of the matrix. Then the Shintani zeta function set A admits a meromorphic continuation to set N with possible singularities located on these hyperplanes. Okay, the hyperplanes described here. So let me explain what each of the elements of these equations are. So notice that each of these C sub capital J, it's a polynomial. And for each of these polynomials, we consider their Newton polytope plus Rn. And these mu kj's are the inward vectors of this face, of this set we describe here. The new kj's are as before, so also described by the hyperplanes, by the half spaces which induce this. It's not longer a polytope because it's unbounded, but this region. And L is just a non-negative integer, so for every L non-negative integer. So let me once again explain that with a small example. So if A is this matrix, then the linear forms we had before, so the C sub capital J's are these three. Capital J could be the set with only one, the set with only two, or the set with 1 and 2. So for the set with only one, this polynomial is just the linear product, the product between this column and the vector epsilon 1 and epsilon 2, so just E1 plus E2. For the second column is just epsilon 2, and for the C1 and 2 is just the product of these two previous ones. And here, what the theorem says is that the poles of the Shintani zeta function related to this matrix A are just given by the facets of each of these three regions. So for instance, let's take this, which is the biggest one, the most interesting of these three polynomials. So the Newton polytope of this polynomial here is just a line segment that goes from 1, 1 to 0, 2, so this line segment here. Then we add it with R2 plus, and we have this blue area here. And then the Shintani zeta function admits a meromorphic continuation where the hyperplanes, the poles are contained on these hyperplanes, which are parallel to the facets of this blue area here. Here I only draw it for this polynomial. I'm missing the drawing of these other two, but when one works it out, we see that here are all the possible poles. The last thing I forgot, I didn't mention you in the last slide, so this here, is that whenever these mu kj's are so plus or minus one of the canonical vectors on the canonical basis, then only the hyperplanes where L is between 0 and nu kj minus 1 carry poles. So for instance, in this case, we only have this pole. We don't have a pole on the x-axis, and we don't have any more poles here because they cancel with the poles of the gamma functions. Well, and that is the main theorem, and that's, I think it's, well, I like it very much, not only because it's part of my PhD, but also because it relates the pole structure of such Shintani zetas with a geometric, we have a geometric description of the pole structure. So a bit, what I'm going to tell you what I'm planning to do next. So first is that with this pole structure, we can have a very good description of the meromorphic germs. So we have Shintani zeta functions. The Shintani zeta functions, we can consider the germs that contain the Shintani zeta functions on zero, and we have a very good description of the algebra of germs which contains such zeta functions. And this is a step forward to, well, to renormalize such Shintani zetas on the hyperplanes, on the poles. Because, well, we can already know which type of poles we have, and then we can start to split the holomorphic part and the polar part of the germ. And another point which I'm working on right now is that as the Shintani zeta functions are a generalization of the multi-zeta functions, and it is known that multi-zeta functions satisfy Stoffel relations, we can generalize those Stoffel relations to this Shintani type of functions, and well, and I'm working on that to describe that such Stoffel relations in terms of Shintani zeta functions. Well, and thank you very much for your attention. This is just the reference.
A naive question. Can you express, of course, these, I mean, you mentioned at the end the Stoffel relation and so on. So can you express these values of this Shintani zeta function as iterated integrals, also like a multi-zeta function? Or?
Well, I'm not I'm not sure that would be interesting. So one way of understanding the Stoffel and the multi-zeta functions is a very ugly way to understanding. Is just that you subdivide the domain of the sum into different smooth cones, and using the inclusion-exclusion principle, then you get those functions. Well, I'm not sure. I really don't know.